Okay. All right. Welcome. I'm happy to have this opportunity to share with you uh, an introduction to blockchain and and smart contracts, which are a special type of blockchain. And this is going to be more of an introduction to blockchain. There's just so much information out there. It's a new and emerging technology, and I thought it would be good to share with the rest of the industry what blockchain is, well, within the rest of our part of the industry, what blockchain is and how it operates. And to introduce the topic, I wanted to share a video here.
When people buy, sell, or trade in their mobile devices, they're probably being ripped off. A pre-owned mobile device can hold a lot of value, but good luck trading it in for a fair price. Why? Because what you don't know is that once your device is traded in, it goes through an average of 7 middlemen. This ends up costing the final buyer up to 50% more than if they bought the device directly from you. And if you choose to take a trade-in price, it's only good for store credit, meaning you'll likely get locked into a new long-term contract and pay full price for a new device. You just can't win. Until now. Introducing Tesa-B, a blockchain-enabled ecosystem that creates a better, more transparent way to buy and sell mobile devices and services without the usual hassle or cost. How does it work? It starts with our mobile app, Tesa-B Connect, where you can test your device's condition. From there, you can sell it directly for cash, not store credit. There's also a trade-in option, where our e-commerce partners like Glide give you credit towards a new or high-quality pre-owned device, saving you up to 50% compared to buying new. And any device that passes our diagnostic tests is eligible for Tesa-B Protect, our accidental damage protection plan. That's pretty hard to find. All these activities earn you Tesa-B digital assets, which you can use toward purchases or upgrades within the Tesa-B ecosystem. Finally, all device grading data and transactions get recorded within the Tesa-B blockchain, permanent, immutable. This means you'll never need a receipt for a damage claim, and you'll always be confident in what you pay and get paid. And it means the mobile device industry gets a secure registry for truly transparent sales. We believe people deserve an easier, more transparent, and affordable model for mobile device ownership. It isn't just smarter, it's revolutionary.
Okay, so this Tesa-B company is just one of many new startups that are latching on to blockchain and leveraging this new technology. To me, it's a fascinating business model. They've essentially created the Carfax for cell phones. And if you're not familiar with Carfax, those people outside of North America, what Carfax is it's a service you can subscribe to and get a report for a used car, and you can tell if that used car has been in an accident, if it's been refurbished. You can know the history of that used car. Well, the same thing can now be found out about a phone. When you go to buy a pre-owned phone, you can know whether it's been dropped, whether it's been dropped in water, the screen's been replaced, if the battery's been replaced, if it's going to meet your needs. So this is just one example of many new startups within our industry, the telecom industry. So today, I'm going to go through an introduction to blockchain, what its functional components are, and then I'm going to show you a demo of an actual blockchain that I have running here on my local machine. So blockchain, it's been around for almost 30 years now. The concept of a blockchain started in the journal Cryptography in an article written by Scott Sternetta and Stuart Habersh. And they were looking to determine the provenance of documents and ensure that they hadn't been modified or changed in any way. And they struck on two key concepts. The first was time-stamping the documents, and the second was being able to link those documents together using cryptography to ensure that they, through cryptography, haven't been modified in any way. and then added to that, distributing, the record of all those changes on a distributed ledger and a peer-to-peer network. And then a couple of years later, another gentleman, Satoshi Nakamoto, came along. He's most well known for his involvement with the Bitcoin blockchain. But he had the idea of introducing mining. Basically, it was a way to ensure that as new blocks were being added to the blockchain, that they were being added in the right way and that they were being validated. And they weren't necessarily consuming a lot of resources, computing resources frivolously. So what are the functional components of a blockchain? These are the 5 main components of a blockchain. First is using of hash cryptography. And the SHA-256 algorithm is probably the most well-known algorithm used to encrypt these documents. It's an encryption algorithm developed by the National Security Agency over almost 30 years ago. It's been around a very long time, very well known to the public. It involves, blockchains also involve an immutable ledger. So a copy of all the transactions that have, and all the blocks that have been added to a blockchain. That ledger and copies of those chains are then distributed on a peer-to-peer network. And as new blocks are added, they're added through a process called mining, and I'll talk about mining in just a moment. And then there's a consensus protocol. And this consensus protocol ensures that blocks are added in the correct order and that they're validated. As different nodes are operating around the blockchain and creating new blocks to add to the chain, there's certain protocols and things that need to transpire in order to ensure that they get added in the right way. So the blockchain, the most fundamental component is the block. And what is a block? A block can be any document, any record. And what happens within a blockchain is that block is then encrypted, and there's a hash value that's created. That hash value essentially is a fingerprint, and that fingerprint gets persisted and attached to every single block. Every time somebody adds something to the chain, their fingerprint is added to the blockchain. Now, this SHA-256 algorithm, it's unique in that it can accommodate any type of document. It can be a video, it can be a PDF, it can be a audio file, a zip file, anything of any size can be condensed down to a 64-character hexadecimal string. And that's what that hash value is following the SHA-256 algorithm. This fingerprint then gets added to each block in the blockchain. So the first block in a blockchain is called the genesis block. You start off with that initial piece of information, and then that information is hashed, and you get that original hash value. As you add the next record to your chain, that original hash value is persisted, and then as the new information is hashed, yet a new hash value is created, and then that hash value is persisted to the next block, and so on and so forth. And so you're able to look at those hash values and see how they're linked together in this blockchain. This blockchain is then replicated throughout the network, and so copies of that blockchain are going to show up all over the place. And there's Bitcoin, there's Ethereum, there are lots and lots of these blockchains out there. Now, as a reward for adding a new block to the blockchain, miners receive a virtual currency. They receive a reward for using their compute resources to authenticate and validate that information for the new blocks that are added to the blockchain. There are currently over 5,000 different virtual currencies, virtual rewards that miners receive, and more of these cryptocurrencies are being added all the time. So what is mining? Well, mining is a process of authenticating or validating a block as it's added to the blockchain. And it's essentially a cryptographic puzzle. It's very hard to solve, but really easy to verify. And what they're doing is they're looking for this nonce value. A nonce is a number only used once. It's a random number that's added to the block, and it affects how that hash value is created. And what they're looking for is they're trying to solve for that nonce value, finding the nonce value that then generates the hash value that's as close as possible to the previous hash value. And there's different degrees of difficulty that they can apply to these nonce values. They can be small nonce values, very large nonce values, to increase the amount of difficulty in solving for that new hash value that they're searching for. And it is seemingly random. If you were to increment that nonce value by, say, 1 digit from 8903 to 8904, in this example, it will drastically change what that new hash value is. Okay, so mining. When they're mining, they're not just solving only for the nonce value. There's several other requirements, a long list of other requirements that they need to follow. But here are like the top 5 things that are involved in hashing those block values. One is that this hashing algorithm only works one way. You can't take that 64-character hexadecimal hash value and recreate the original document. It just doesn't work. It's deterministic also in that when you apply this hashing algorithm, you always get the same result. It's not like you take the same document, apply the same hashing value, and you get same hashing algorithm and you get a different value. You always get the same hash when you apply it to the document. Fast computation, it's hard to solve but easy to verify. There's an avalanche effect. That means that in that blockchain, if you were to go back to a document upstream in your chain and you were to modify it anyway, let's say add a space at the end of a sentence, that hashing algorithm is going to change, and all the other subsequent downstream hash values in your chain are also going to change as well. And so that makes it very easy to identify when someone's tried to modify or change a document in the chain. There's also a consensus protocol that helps the blockchain withstand collisions as different nodes are adding blocks to a blockchain. Two of the things that they look for is looking at the length of the chain. The longest chain wins. If there's another node that has a longer chain, it's more well established within the network, then that's going to take precedence over a newcomer to the blockchain. And then also they're looking at the majority. So as blocks are being added to the chain and that chain's being replicated throughout the whole network, if the majority of the nodes on the network dictate that that this new block should be added, then that'll take precedence over a new and up and coming block that is ready to be added to the chain. So those are some ways that the blockchain withstands collisions, and there's much more. Now, I mentioned before that the miners are competing for that they get rewarded, and so in this example for the Bitcoin blockchain, what happens is that new block comes up and that new information is ready to be added to the blockchain, then all the miners compete against each other in order to be the first to obtain that next reward. And as a result of that, it consumes a lot of resources. The way the current Bitcoin algorithm is set up, you've got miners, millions of miners all around the world with millions, tens of millions of these mining rigs set up, all competing at the same time for that next to receive that reward for that next block to be added to the chain. And that consumes a lot of resources here. I was surprised to learn that a year and a half, almost 2 years ago in 2018, Bitcoin miners alone consumed 54 terawatt hours of electricity. That's the same as 5 million US households for an entire year, and the same as all of the electricity consumed by New Zealand or Hungary throughout the whole year. So you have to question whether this business model is really sustainable. As a result of that, there are a number of alternatives being proposed throughout the industry to deal with this issue. A lot of them are focusing on being able to distribute who has the opportunity to mine that next block and receive that reward. There's a thing called proof of selection, where in a pseudo-random fashion, different individuals are given that opportunity to add and compute for the next block instead of having everybody competing at the same time. There's an algorithm called proof of stake, where you put up a little bit of money in order to increase your chances of being that next one to solve for that next block. There's an algorithm that's been devised by Intel that's called proof of elapsed time, where it randomly divvies up the compute resources across the network, so that all the network isn't always computing at the same time. There's a number of additional hashing algorithms. One that does a lot of the processing offline in a mirror type network. Another one that solves just for the nodes around itself, rather than trying to keep the whole chain linked together. So the point behind all this is that it's still early on in this technology. There's still a lot of things that are being worked out. I read recently an analogy to where the internet was several years ago. The blockchain is kind of like when TCP was first being created and developed for the internet, and so there's still a lot of things that are being worked out, and so it's just a matter of time until one kind of bubbles up as is how it works. Now, it's fine to talk about blockchain and the functional components and how it works. I thought what would be really good is actually to show you a demo. That way it makes it a little more tangible, makes it more real. So I've set up a demo here, so working on my local machine. This demo, I'm going to show how I'm able to send information through a blockchain from carrier A to carrier B through a 3-node network. I'm going to pop out here, and I'm going to go over to my demo here. And so to start off with, I need to establish my network. And to establish that network, I've established 3 nodes at 5000, 5001, and 5002, and then I've linked them all together here. And I've already set up my Genesis block. I've already added some information to that blockchain. Next, I then add my clients to the blockchain, and the first step is establishing a public and private key for each of my clients, and I use that information to send information back and forth to each other. Okay, and I pre-populated this. I populated for carrier A, I populated their public key. I've populated their private key, and then the public key of carrier B, where they want to send this information. And they can really send any information that they want. In this case, I'm going to send some pricing information. It includes the description of the product, the capacity, bandwidth capacity, the pricing, terms and conditions. Really anything can be added to that block. A PDF contract, a audio file, anything. So I've added that to my block here. I'm going to say generate transaction. It's going to ask me to confirm the details and have me put in which node that I want it to be recorded on, and I click confirm transaction. There you go. So now I'll go back to my node here, 5000, that was linked to carrier A, and I'll click refresh, and there's that new block ready to be added to the chain. Now it's not yet been added to the network. I have to first mine that information. It creates that hash value and has now added that new block to my chain. Now my other nodes, they don't see it yet. I need to refresh those other nodes as well. And go back here, refresh. Okay, so now all the nodes on the network have the latest, greatest copy of the blockchain. And next I'll go back to my carriers here, and I'll click view transactions, and here it is, carrier B. Now can see that information that was sent to them, and then they can respond back. They can send information back and forth to each other now that they have their they're able to share their public and private keys, and they're connected to the network here. So a very basic, simplistic illustration of a public blockchain. This only took me an afternoon to set up. Very easy to set up these blockchains and get them running. Okay, I'm going to go back now to my presentation here, and okay, let's talk about use cases in blockchain. There are dozens of different use cases that I've discovered that are being implemented within blockchain. Here's just a list of some of them. I'm not going to read all of this information. A copy of this will be distributed after the presentation, and you'll be able to go back and read this and look at it more closely. The blockchain, it's used primarily, these are some of the major issues, and I will read just the headlines. It's used for digital asset transactions. Think about micropayments. Instead of sending, you're putting in your phone number, which we know can be easily spoofed, you can put in your private key information, and that is something that's unique that only you will have. Many people are, using the SIM card as what that private key looks like. It's used for inventory management through the use of smart contracts, and I'll talk about smart contracts in just a moment. Used for digital identity management and verification, used for fraud prevention and cybersecurity. Again, instead of putting in a phone number, you can put in your public and private key information on the blockchain. It's used for roaming settlement. I'll talk in just a moment about what that use case looks like. Used for fraud prevention and IoT security. And IoT seems to be where it's being adopted the quickest within our industry. They're using blockchain in order to ensure that the different IoT devices are able to connect back to their home networks, and that other devices aren't trying to latch onto these IoT networks. Okay, so smart contracts. we'll talk just a moment about smart contracts, and here I have another video to share with you that gives a good background and an overview of what blockchains are. This comes from the Ethereum network.
What are smart contracts? A smart contract is an application that runs on a blockchain network. Developers write these contracts, then deploy them to a public blockchain network where people can interact with.
All right, let me try that again.
What?
All right, the video is not working here. Let's see if I can. Actually, we'll just move forward. So a blockchain smart contract, basically what we do is we take these contracts that are written in human language and we instantiate them into code. That code then is uploaded into the blockchain and essentially is a distributed application that sits on the blockchain. Then as information is sent to that special node, then the instructions that have been programmed, will self-execute. Let's say we've reached a specific billing date. Well, that trigger then would execute the smart contract to go back and do the billing, or really to do whatever instructions it's been programmed to do. Sometimes it's to release funds. Other times it's to execute a machine learning algorithm, robotic process automation, or some other process. And the great thing about these smart contracts is that these documents are, the history of these transactions is always recorded on the blockchain. So an auditor or a regulator could go back and they can see what transpired as a result of the contract on the blockchain. Here is an example that you might be able to appreciate this through. I was surprised to learn that the music streaming industry has been using smart contracts for quite a while. You pay your monthly fee, and in return you're able to listen to an unlimited number of songs throughout the month. What's happening behind the scenes is these smart contracts are keeping track of what songs you're listening to. And then at the end of the month, it goes back and it sees who the artist was, what the song was, and then it can look up what the corresponding royalty payment is. Now that royalty payment is not, they don't just send like a lump sum and over to the artist. These contracts can actually be really quite complex, and they can split up those payments, so that so much goes to the band, so much goes to the songwriter, the singer, so much goes to the promoters and the distributors, all that information. And as you think about it, you've got tens of millions of subscribers, hundreds of thousands, or millions of songs, thousands and thousands of artists. That's a lot of complexity, a lot to keep track of. Yet the smart contracts are able to keep track of all of that and execute automatically, which is really impressive. Another example, more closer to home, within the telecom industry, is how smart contracts are being used within the roaming industry. Traditionally, you had clearinghouses that sat between the different roaming partners, and they kept track of the voice and data usage that the roaming partners were providing each other's subscribers. That is going away, and it's being replaced with a blockchain. Now through a blockchain, the amount of voice and data usage being consumed by subscribers as they're roaming on other carriers' networks, that's all being recorded in real time on a blockchain. And the operators can then look back onto the blockchain and see in real time how much usage has been consumed, and then they can do settlements, real-time settlements, or and they can even modify those contracts on the fly if they want to settle up sooner than waiting to the end of the settlement period. There are a lot of benefits for smart contracts. One, it's a low transaction fee. You're not having to stand up a large data center with a lot of hardware. A lot of these blockchains, especially the public blockchains, can be set up within a matter of hours, and you can have your own blockchain going. And then to make an update to a smart contract or add a new block to a blockchain, it only costs a fraction of a penny. So very low cost transaction fee. Because it's on a distributed network, around the internet, the whole internet would need to go down in order for your application to go down. And so the chances of that are very slim. It's immutable in that, because it's recorded out there and replicated, very low risk of those contracts getting modified or things getting bumped along the way. It's completely autonomous because it's an application and not a human. Those contracts can operate automatically. It's quick. Instead of taking days, weeks, or months to review contracts, those contracts can be executed nearly instantaneously. There's a huge cost savings that come from smart contracts. Again, you're not having to hire and maintain staff. That this can all be moved on to a computer to handle. And again, because it's not involving humans, the accuracy goes way up. There's a lot fewer chances for errors. It's completely trustworthy, and it's backed up. The information won't be lost, and it's encrypted. I mentioned public contracts, but there's public blockchains, but there are also private blockchains as well. Information on a public blockchain can be encrypted, and so you can preserve who's able to see what's in that information, or if you don't want to take that risk, and you can also set up a private blockchain where only the two parties have the ability to see what was transpiring there. Now, there are some challenges with smart contracts that you need to be aware of. They can become extremely complicated. If you've ever gone back and read a master services agreement, or even the terms and conditions for your cell phone, there's a lot of legalese that you have to read through. But there's ways around instantiating that into code. One of those is using artificial intelligence and computer vision and robotic process automation. You can use computer vision to read through those contracts and extract that information and populate it into the necessary reference tables and templates that you set up for your smart contracts. There are software programs, and anybody who's written a software program in the past, sometimes bugs get introduced, and so you need to think through about how would you modify those smart contracts? How would you mediate if a bug was introduced? Now, fortunately, when bugs are introduced, the cost to fix them is really quite low, in that it's only fractions of a penny to change the state of those contracts on the blockchain. That said, there are some risks to these contracts. If they're written very poorly, you could expose yourself to a lot of liability. These contracts work best with IoT devices. IoT devices are also known as oracles, and they're the way that these smart contracts interact with the physical world. Think like a smart lock. A payment is made, and then instructions are sent from the smart contract to that IoT device to unlock and to release the key to the rental or vacation home or whatever it is that the person is receiving in the physical world. But because of that, that does create a single point of failure, and so you need to think through, well, what happens if the network goes down, or if connectivity to that specific IoT device goes down? How would you remediate that? And then the other big challenge that you need to think through is, what if the party puts in wrong information? They just get the billing address wrong, or the service location wrong. Then how would you remediate that as well? And so, and there are ways around that. You can, again, easily modify those contracts, make the changes that you need in order to get everything in line like it should be. Okay, so we're coming to the end, and I want to tie this all together. Using blockchain, we can start to link everything together. Now, when you think about our fraud management systems today and our revenue assurance systems today, they're pulling data from lots of different places, different systems, and in different formats. Through blockchain, we can now start to link all this information together ahead of time. You can pull subscriber information and usage information, and then have smart contracts begin to monitor all of that automatically. And then those smart contracts can be integrated with machine learning and robotic process automation. So if the machine learning algorithm, like a fraud management, fraud detection algorithm detects that fraud is occurring on a subscriber's account, then it can automatically execute and take action to mitigate against that risk. Further, by linking these smart contracts together, one smart contract can call another smart contract, which then sends out an alert to the customer, sends out an alert to the fraud analyst, and it can call yet another smart contract to generate the subsequent fraud reporting. And so when I think about the future of fraud management and revenue assurance, I see a completely new world of possibilities. I see the way that we operate. In some ways it will stay the same. There'll always be fraud. I think it'll be the same types of frauds, but I also see the way that we operate changing considerably, using these new technologies in combination with each other. Okay, and so with that, I will stop and see if there's any questions.